Now, what about all the content you've covered now from chapter 11, 12, and 15 is the most difficult? Not a specific question, but a type. Is there a set of problems that you come to and you're like, I have no idea where to start? Is it mechanisms? Is it memorizing the reagents? Is it what thing comes to mind? Okay. What about mechanisms specifically? Where to start? Where to start? What attacks what and why? We'll discuss. Okay. Okay. Let's take an example. Let's take a simple example. This is from chapter 12. Can the people here see me? Online, can you guys see me? Reaction of an alcohol. We want to convert an alcohol into an alkyl halide. An alkyl halide is a fancy way of saying a long chain of carbons with a halogen, bromine in this case. The one reaction you cover is PBr3. The mechanism may look complicated on your slides. Let's break it down. Back to the analogy where Susi was standing up here. What do we want to convert? Step one, identify what is it that's changing on your molecule. I always say start left to right. Read from left to right. Is this C changing over here? CH3, CH3. Is CH2 changing? Is OH changing? Okay, what is it changing to? Br. So we need to somehow replace our OH group with Br. How do we do that? We look above and below the arrow. Above the arrow, what do we have? I expect you, PBr3. Okay. Below the arrow, nothing. So we're just dealing with PBr3. What's special about PBr3? Well, it has the bromine that we so desperately desire to attach here. And we want to get rid of this OH. So find your functional group, which we found is the OH group, and we're replacing it with Br. To start this reaction, always remember oxygen has lone pairs of electrons, 2 lone pairs of electrons, that are readily donatable, meaning if there is something in solution that's ready to accept those electrons, oxygen is like, here, take them. What is in solution that we have, that we've identified? Look above and below the arrow. What do we have? So the only thing that those electrons can go to is PBr3. So let's do that. Let's draw our alcohol donating these electrons to PBr3. Let's first draw what PBr3 looks like. It's very simple. It's phosphate. It's P, phosphorus, Br, Br, Br. Okay. Let's draw the electrons that oxygen so readily wants to donate to phosphorus. Why phosphorus? You'll see in just a second. When we donate these electrons to phosphorus, we're building a bond. So phosphorus, in theory, would have how many bonds? 1, 2, 3, 4, in theory, if we allow them to connect. But everything about mechanisms, this is an important thing, everything about mechanisms is what's the most productive step that we can do in solution to get to where we're at. What's the most productive step? Science has shown us that this bond or this bond or this bond, one of the BRs is going to leave solution. We break. We break this bond. You can choose this bond or this bond. Symmetry. It's the same thing. Let's redraw everything. Redrawing and reading always left to right, so you can keep track of what's changing and what's not changing. We have CH3, the same. We have CH2, the same. Okay. Something happened at the O. Let's draw our O. Let's draw our H. And what do we say? We built a bond between oxygen and phosphorus. Everyone tracking with that? Perfect. We kicked out a Br. Perfect. So that means our PBr, what? It's going to be PBr2 or 3? 2. It's because we just kicked out one of these atoms. So let's do that. PBr, Br. When we kick out Br in solution, there are electrons in this bond. This bond, if you want to redraw it, literally looks like this. P, 2 electrons like this, Br. They're sharing. This arrow indicates that Br has readily accepted them. So it's holding onto these 2 electrons, like these are mine now. When I hold electrons, what's my charge? Minus. Very simple, minus. So we're going to do plus Br minus. Okay. One thing that gets people tripped up with mechanisms is the charges. Charges tend to change, and it seems freaky and funky, but whenever you see a charge, if you have a plus, you need to have a minus. If you have a minus, you need to have a plus. How do I know this? Look at the structure here. Do you see any pluses or minuses? Which means the overall charge is 0. We have a minus, which means we need to have a plus somewhere. How do I know where that plus is going to go? Oxygen here had how many bonds? It had one with the carbon, and it had one with the hydrogen. When oxygen has 3 bonds, it has a charge of plus. How do I know this? I don't memorize it. I just remember H3O+. Oxygen here has 3 bonds. It's plus. Okay? You don't need to memorize that weird table that he gives you in the beginning of chapter 11. So we're going to have to put a plus here. And of course, we still have our lone pair. Abdelhamid, where did the lone pair here go? It's this bond. Okay. What did I say about mechanisms? What is the most productive step that's going to get us from where we're at here to here? We want to replace what? OH. What do we know about OH? It's such a difficult group to remove to begin with. Back to the analogy with me and Susi. Susi is the OH group. He doesn't want to leave. So what did we do? We tickled him a little bit. We were like, beat it. I'm not going to swear. Beat it. That's what we're doing here. We're making this bond right here, which is typically super strong, slightly weaker, and more susceptible for attack. Attack by what? Br. Where do we have Br in solution? So what's Br going to do? It identifies, it doesn't actually identify, but I'm just explaining here. It sees that this bond is super susceptible. And it's like, oh, okay, that's super simple. Br will come in, attack this carbon. Carbon can have a maximum of how many bonds in organic chemistry? This is the ultimate sin. 4 bonds. If you have 5, you go to hellfire, straight. Carbon needs 4. If we build this, it has 5. What's the most susceptible bond that we just talked about? This one. Everyone with me? If I'm moving too fast, let me know. This bond is going to break, and this whole group leaves. Let's redraw our final structure. Everything in solution. Everything in solution. Left to right, we have what? CH3. I want to hear you guys say it out loud. CH3, CH2. Then what do we have? What did we just attach? Br. And we kicked out this whole group, which is what? Which is PBr2OH. Have we not successfully demonstrated a valid mechanism that takes us from our alcohol to our alkyl bromide in what? 2-3 steps. Break it down like this in English such that it makes sense to you. That's all of mechanisms. Notice how we broke it down into 4 or 5 steps, mental steps before we started. Step 1, what am I dealing with? What's changing on the molecule from start to finish? In this example, it was 1. It's simple. What's above and below the arrow? Meaning these things are definitely going to participate in the reaction at some point. Perfect. We said it was PBr3. The goal is to convert OH into an alkyl bromide. Great. We demonstrated that this is the bond that we need to break. But it's too strong as is. So we need to give that OH group a reason to get out of the molecule. That reason is donating to PBr, but PBr does 2 things. 1, it weakens that bond. 2, it gives a bromine. That bromine comes back in, attacks. This bond breaks because it's the most susceptible one, and we have successfully formed our alkyl bromide plus PBrOH.